All right, I'm back, and I'm going to keep working on the problem sets that I was working on before. Just for those who are tuning in right now, to kind of let you know where I'm at with an update. Let me just switch over here, view here. What I've been doing is, after I finished all the lectures and finished all the problem sets in the first pass, I decided to go through all the problem sets and try to identify what were concepts or ideas or skills that I was not as well practiced in, which was interfering with my ability to get these questions right. So what I did is I split it into two parts. So I had this part where I wrote down ideas, and you can see I've crossed out quite a few of them, which means that I have gone through and covered those since then. And I also have some questions up here. And so I rewrote, so the circled ones are ones that I had not done for some reason the first time. And then I crossed all of these out when I've done them for a second time. So we were working through this right here, and I think I was just finishing, oh yeah, this was I was on 3.2 F, I think, when I left for today. So what I'm going to try to do is just see as far as I can get through this. I am trying to really push myself because I have seen these problems before. So this is, again, something that I should be able to handle. Now, one of the things that can often happen is if you're facing something that is above your difficulty level, you can get feedback on it. But because there might be too many things going on in the question, it's often not possible for you to necessarily recall exactly how you solve all the parts of the problem. And so this means you can do it again later and still get it wrong, which is sometimes what happens. But the thing that I find is that if you do it a second time, you're probably going to remember a lot more. Now, just doing these questions over and over and over and over again until I'm doing them all perfectly would not necessarily be the right way to master quantum mechanics, because these questions are really just a subset of what I should know in this class. Now, they're pretty broad, and I think if we're thinking at the higher conceptual level, they do have pretty good coverage. So I'm not too worried about that, but definitely if these questions were more on the calculating end, so like, getting particular answers to particular questions, I would have to be careful that I'm not just sort of memorizing, this is how to solve this problem, this is the trick behind this problem, rather than looking from general principles. However, on the other hand, the way that you build up knowledge of principles is often by learning a lot of tricks. So I think there's kind of a balancing point. On the one hand, I want to go through this and really feel like I understand the problem sets, and that's likely to help me on the exam when I take it. And on the other hand, I have to be aware of what's missing from the problem sets and what kind of knowledge do I want to fill out. So I kind of go back and forth between doing questions here, and then if there is a trick or if there is some idea, I try to figure out what is the generalized version of that idea. So in the first question, for instance, this wasn't even quantum mechanics, it was just classical mechanics, and it was an electron orbiting an atom, and because it's an accelerating charge, it is radiating off light, and so it's spiraling into the proton, and it's to figure out, how long does that take? And this was, had a specific form, and I tried it, and I didn't get it right, and I looked at the answer. And I could just try to memorize, oh, this is how you do this problem, but really what I see this is a more general part of the issue of setting up and solving differential equations. So learning how to set those up and making sure I'm doing them right. Now, this is something I've studied before, so this is something I have zero experience with, but being able to think through, okay, here's a word problem, how do I put it in the form of a differential equation, I think is important. So what I'm going to do right now is just keep working on this. I'm going to go back to this question. I had kind of paused at 3.2F because I felt like I should be able to answer it, but I wasn't quite getting it right. And so I'm going to go back to that now and keep working on it. And I'll just sort of see how far I can get. I mean, I just started doing this stuff. What did I do? Did I do this? I think I did that stuff yesterday. So I think I did this morning. So I've been kind of going through it at a decent pace. I figure if I keep this up, I should definitely finish through this first pass by Friday. And then hopefully that plus some of this, that'll take me to the end of the class, and then we'll just see how well I've done. I mentioned before, this class has been very difficult for me. There's been a lot of questions I've struggled with. Some of that is weaknesses in my background, and some of this is just the difficulty of the class. So, I don't really know how things are going to turn out. So this is kind of exciting for me too, because if it was something where I'm like, okay, I know this, I know I can get the exam done long before the class is over, then there wouldn't be much need to do this kind of thing. But this here, because there's a decent chance that I won't be successful at passing the exam, then it actually really tests you of, what's the right way to proceed through this? How do you not waste time on things that don't matter? So with that said, I'm going to shift over now to setting this up. Hold on a second. All right, so let's go back to this problem and let's remind ourselves, let me remind myself how this problem works. So what we're looking at for f is we want to see how the derivative operator acts on the Fourier transform of a function. Now, I'm thinking that the answer is going to be something simple. I don't know exactly what the form is going to be, but I think it's going to be like ik. That's my guess. Or maybe it'll just drop down an I. Maybe. Okay. So yeah, because we know when we drop down, what was it? We know from the last one that when we take the momentum operator is just like the x operator. So when we apply it, we get the momentum, which is k, and then IH bar. So I think it's just going to drop down IK here like this. So it's something like this. So if we pull this into the, I see this is, I don't know, I'm not quite as confident in this. So this is, we're pulling in this here. So we got dx, and then we take this was our, we wanted to have this in terms of k though. So let's do it with dk. So we want to go this minus dk, and then we're going to go d dx. This is e to the minus I kx. This is plus I kx now. So this will just take down ik. And then we're taking this derivative. Which I'm pretty sure is just ik f tilde. Right? Like crazy here. I'm doing something wrong here, so. Okay, let me just restate the question so that I can make sure I'm doing this right here. So we have hi, Katya. 1 over root 2 pi. And then we want to do this on both sides. So it is over this X domain. Dx and then ddx. So I think these will cancel out by the fundamental theorem of calculus. We have e to the I of kx fx. And then let's replace this e to the minus I kx times Okay. And I should be able to, can I bring that in? There's a K on the outside there. Yeah, I don't think what I'm doing is working. I am not sure whether I'm any further than I was before this morning when I was looking at this. Yeah, I'm going to go switch to the answer now. So, yeah, so I did get the right answer, but this wasn't the logic. So let me just put these things together. So we have T, L, F, K. Two, one, D, okay. And then this, T, L, F, K, equal E to the I, L, K, F, okay. And then we divide out. So we get D, F, K, I, K. All right, that was actually easier than I thought. So let's shift over now. I think I had for my next one I wanted to do was H. So I want to verify that the commutation relation dx equals to 1, whether acting on f or its Fourier transform f of x. I think that what I argued the first time around is that commutation relation is invariant to what you apply towards, so it shouldn't matter. But I think that what I was missing there was that this is not f of x, it's f of k. So, and then the answer was that Fourier transform is a linear operator. Or that it, oh no, the Fourier transform commuted with those. So hold on a sec. So we have D x to 1, and we want to ask what's dx Fourier transform. So this is d so x on the Fourier transform should I put this all out? I think I see. Why isn't this? This must be true, right? See, I think this question I was getting it wrong because I didn't understand it. Because this would be true of any operator, so I'm just trying to think of what they're asking specifically here. E to the kx f tilde of k minus So if we do this, we get, let me just put this up over here. So ddx of this is going to be plus, and then okay, and then this one minus x EIKX delta of k. So this cancels with this. We get this is our original f on f of x. So that should be true. So we did it a little differently. They did, what did they do? They did and k is equal to ik I dk I d. Yeah, I think this is right. I'm going to just say right, even though I didn't do it the way they did, because otherwise I'm going to drive myself crazy. So, going back to our thing, I've now finished these guys. So I'm on to 4.2. All right. Oh, this is the thing that we already did. So I'm not going to do this 4.2 A and B because I just did this one. Yeah. I did this one when I was looking at the real eigenseed. So let's go to 4.4. 4.4, all of it. And this is new. I did not do this one. Play around with this. Oh, there was an applet. Do I have this applet? Let me look. Do I have bound states? I do have this one. Okay. Let's open it up. I'm going to switch the window. Do I have one set up for it? So I'm going to just do this while I'm playing around with it. Maybe I'll just read out the question. It's on the problem set. Consider a particle of mass m that is in a superposition of the first two eigenstates of the infinite potential well of width L. Play around with the quantum balance state applet for insight into the system. Build the above superposition state and watch the system evolve. Print a screenshot of the superposition, including your problem set. Experiment with other superpositions too. So let us do that. We want this height to go. Can we make it go up? How do I change the height here? Height. Yeah, this is maximum. Do I have, this is just one well. I think this is, yeah, they don't have an infinite well here. I mean, as this goes higher, but when we get to the top bound states, it's going to be less and less accurate. I guess if we consider a very narrow well and very high, it's going to be close to infinite. And what do we have? We have the two. All right, that's pretty much what we expect. This guy. It's kind of cool. If you look at this like just with the right eye, it looks almost like these are at right angles to each other and it's rotating, hey? And if you look at it right, it's kind of hard because these are actually two, but if you just imagine it, like these are at right angles from each other, it kind of looks like that, right? I mean, this one too, but it's happening faster. And this one 3, but it's happening so fast that... All right, that's probably all I want to do for this. Let me just go and I'll switch back to the problem set. So let's go to B because we just kind of did a verify that psi x of t is properly normalized and remains so for all times t. Well, I mean, this is a pure phase, so I don't have to worry about that for times this t part. So we just have to look at equal to 1 over L sine root 1 over L sine 2 pi for Lx. And we'll just take norm squared of this. And we can do with the phase. So let's just go, let me write that all out then. So we can just go between 0 and L. And then this is going to be root 1 over L. These are real, so it's just going to be a square. So we're going to have root 1 over L squared sine squared pi over Lx. And then this is e to the minus 2I w naught t. And we have the cross term, which is 1 over L squared sine pi by Lx sine 2 pi by Lx. And plus this final term, I guess I can just stop writing it with that, sine squared 2 pi over Lx e to the minus 2I omega 1 t dx. And so right away, this guy's going to be 0. We already know that because of these are orthogonal, so this is going to be 0. Contribution of these things is going to be 1. Pure phase. Pure phase. And It's going to be pure phase when we're looking at because that's when it's infinity. Yeah, because it has to be the whole width of it, so I don't think it's going to matter. And so we have 1 over L we have 1 over L so this is just these two things separate. What is sine squared evaluated over? What is that? I think it's 1/2. We have this thing would be, because we have 2 pi over L Sine squared. This is also 1/2. Hold on a sec here. Close this applet. All right. One over L here. I'm missing an L here. I think this has got to be L by 2. I think it's because I'm forgetting the L here. Yeah. Let's see if that's right. 4B. Thanks. Thanks to Dokukan and giveaway. I don't even know what that was supposed to be. So C. Oh, that's A? Oh, that's A, right, B. Yeah, L by 2. I forgot there was an L factor there, right? L by 2. Okay. But I got it right at the end. All right, C. Calculate the probability distribution. This period T of the superposition. Pxt is equal to one over L sine I by L. Oh yeah, these guys cancel because they're opposite each other, right? Because 1 by L sine plus this is squared sine squared 2 pi over L x. I think this is just 1 because I think we can ignore those cross terms because they're orthogonal. I don't know. Let's see, we have sine sine 2 pi x, and then it's times e to the I think that those also cancel, right? Because we have e to the negative I omega and e to the I omega t. No, they don't, because one of them is going to be minus and plus, so it's going to be yeah, cosine of, so if we have e to the it's going to be e to the I of t. This should be cosine again, not t, right? And this should be periodic. How often? Sort of. I am working on a probability distribution, but it is the norm squared of the wave function. So the whole idea behind quantum mechanics is that we don't know what the actual, where the exact particle is. We know we can have a wave function which defines the probability distribution for any function. So I'm doing this for this particular energy eigenstate, which has one guy going like this and another guy going like that, superimposed with each other. And I'm trying to figure out what the period is of this. In T, I think it's omega naught. I think it's this. Oh, right, these are angular frequencies. There's not omega 1, omega 2. I thought it was 2 omega 1. So this is equal to 2 pi, yeah. 2 pi over omega naught. All right. B, C, D. Sketch the probability distribution PT evaluated at time T star. Is it 1/2 omega H bar and equals omega H bar omega? Is that right? No, it is. I'm thinking of central potential. E0 is equal to pi by L squared H bar squared over 2m, and E1 is equal to so we have pi, this is pi divided by the difference between these two, which is going to be this negative negative 3 pi squared over L squared. This is squared. Lose one here. Here it's m L squared over r squared pi. Is this even the right units? So we've got kilograms here, got meters squared here, And here we have kilograms squared meters to the fourth times seconds squared. Doesn't even seem like the right units. No, it's plus this, plus this, plus this. Two times this, yeah. I guess it's 2 times 2 is 4/3. This is 2 energies. I don't understand how to even answer this question. Evaluated at time t star pi by the difference in 2 energies. Okay, I gotta look at this because I'm not even getting the right dimensional analysis. I must be reading the question wrong here. Okay, let's look at what they did for D. Oh, there's supposed to be an H bar there, well, of course. All right. Okay, let's try it again with the H bar. Okay. Jesus. All right, so this pi H bar. So it was pi H bar. Oh, pi H bar over 2 E naught minus E1 and E naught equal to H bar squared K squared divided by 2M. What's the relation K and omega squared? I think this is right. Omega squared. So let's just plug it in right here with the K's. We have these guys, I'm going to have E1 minus, so this is the opposite round. So we're going to have 3 h bar squared equal to this. We're going to have L squared M for pi h bar. Now let's see what we have. We have this is meters squared, this is kilograms. We have kilograms meters squared second. All right, so we got the right units. L squared M over 3 pi h bar is our t, and we want to find at t equals this. What is p of t? So let's just write this up again here. L squared M over 3 pi h bar. And Neat Study Sessions in 20 Days asks Scott, how you deal with theoretical part in studying if there is no concept in that to understand. You're going to have to re-explain your question. I'm not quite sure what you mean the way you've worded it. So our function of p of t how did I write this down? 1 over L sine squared plus sine pi by L x sine 2 pi by L x. And we have where are we? Then we had cosine of omega t, if I'm not mistaken. This should be our density, and we want to sketch this at this time. What is our omega naught? So omega naught is equal to, it's 2 pi over k, if I'm not mistaken, right? K over 2 pi, no. K is distance, I guess. I won't be Yeah, I'm sorry, neat study session. I'm still not quite sure what you mean by a topic. Can you give an actual example of something you're trying to learn that's like this? I don't understand where there's no concept in it. But there are lots of concepts in biology, so you need to be more specific than that. I have no idea what I'm supposed to be doing here. I think we can take En. I'm getting a little bit of brightness here now. So neat saying we should learn biology and ecology. Well, I mean, these are all things that have concepts in them. If there's facts that need to be memorized, then you can do things like flashcards and active recall. But I mean, biology has tons of concepts. So this is going to be this h bar squared k squared to m. And this omega naught is essentially this En. So let me just look at this phase dependence here. So if e to the I omega naught t is equal to e to the I, omega naught is this guy. Oh no, t is equal to this guy, and omega naught is equal to r. It's actually just pi over L squared over 2m. And then this is L squared m 3 pi h bar. I get h bar cancels. L squared cancels. M cancels. One of the pi's cancel, and we have equals e to the I pi by 6 for this guy. And then the other guy is going to be almost the same, but it's twice that. It'll be e to the I. And then for this is going to be cosine of Yeah, I am tired today, Ricardo. Yes, I studied classical mechanics. I did that as part of the MIT challenge. This one is... I think that's right. So we're looking at evaluating this at... So what is this cosine of pi by 6? So we're going to have 3 factors overlaid. So let's see if I can sketch it here. And this is at time equals L squared M over 3 pi h bar. So what do we work here? 2 pi over omega naught. And what is this? Over omega naught. 2 pi over omega naught. Omega naught is h bar squared pi over L squared over 2m. H bar squared pi L. This is 1/12 of t. That would be my guess. And then what does this look like? So I want to graph out each of these separately. So sine squared of pi Lx is going to be like is it concave or which way is sine? Sine squared looks like this, I think. Times some e to the I pi 6. And this one is going to be times and then what's the cross terms? I don't know. The sketching this is going to be me saying I am preparing for multiple choice test examination. Yeah, I mean, if you look on my website, I've given quite a bit of advice on how to study for exams. I don't think there's anything particular about those subjects you're talking about that would necessitate a different approach. So if you look on my website for how to study for an exam, I think that would be the best advice I could give for that. I'm not going to sketch this because it's going to be nonsense, but let's see if I got it right. For the a quarter. How did I get a 12th? All right. All right. Expectation is a function of time. Oh, let's go E first. Yeah, good luck on your exam, Nate. Let's go E. I'm assuming this is going to be 0. It is equal to 1/2. It's not going to hang around in one other part of the well. Oh, I thought it just meant for all t. Let me write this down. This is once. So this is xt left-hand side is going to be equal to 0. So 2L L divided by 2 of r sine squared. Sine squared. My function here, sine squared. There's no independence there. Plus sine squared 2 pi Lx plus we have sine x sine 2 pi over Lx cosine. I think that's right. And so we want to integrate this. This is dx. So we've got this. This is going to be 1/4, but it's divided by L. So this term is going to be 1/4. This term goes up twice. I think this is also going to be 1/4. And then the question is, what does this one evaluate to? So we have 1/2 plus 1 over L. 0 L by 2. dx. I don't really know an easy way of doing this one. Yeah, let's look at what they did. I'm not going to try to haggle over that. Oh, I forgot the 2 here. No, they just evaluated it. So this is just 1/2 plus 4 over 3 pi cosine. Oh, right. Because this these two are orthogonal within that period. Yeah, because it's in that period. So this is going to be equal to 0. Crap. Yeah, I don't know that one. All right. Trig integrals, definitely. So put that there. F. Expectation value of the particle's position is a function of time. So it's just going to have x on everything. All right. Can I do sine x squared? I think I can just do integrating by parts for these guys. It's not the right way to do it. That would be u. That's right, for integrating by parts, right? Gotta remind myself to integrate by parts. right. Okay. So we can do this integration by parts and go over L0 to, this is not L by 2, this is L. No. L of so this one's going to just be x sine squared x L evaluated at 0 and L. I guess I can just put that here because I don't need to copy it over. And then this one's going to be the same, but minus. We take this one as h. X. 2 pi by Lx. 2 pi by Lx. Ooh, this one's going to be tricky. Let's put it over here. Put my dx. What do we have here? This one's going to value to L, and this is going to be L times L there 1/2. So this guy is going to turn into L squared by half minus, we do this one once. Actually, not sure how that works with the double integrated bounds. I think it's just going to be once, which is just now L by 2, right? And I think we're going to have the same thing over here. This thing. This thing, I have no idea. Yeah, I'm going to just shift forward. I'm not going to grind out this integral here. So Afaq Syed is asking how to retain medicine. So I suggest Googling, I think it's called an evidence-based guide to studying medicine, something like that. It's a really good guide for learning medicine. Oh boy. So this is equal to L times 1/2 minus 16 divided by 9 pi squared cosine. Yikes. Be the same thing because there's a node in the middle. Well, if we use the third ground state, it wouldn't happen. Yeah, okay. Now let's look at 4.5. How should I explain myself information to remember more? Subjects like surgery get stuck. So again, I recommend looking at the book that I recommended. You're going to have to memorize things, and for that, I suggest they recommend an approach that's based a lot on spaced repetition systems. I mean, explaining to yourself to understand something is useful for understanding concepts. But if there's a lot of information you need to remember, then you actually do have to memorize things. And if you're memorizing things, then I suggest spaced repetitions or systems are a great way to memorize large amounts of information. So I recommend looking at that guide. They have a lot of useful advice for that. Oh, let's go over to 4.5 now. Oh yeah, qualitative properties. Oh, this is a fun one. So, those integrals were just killing me. So go like this, and our, let's make the function like that, and we want to have a guy here, E naught, and a guy here, E6. So there's going to be no nodes, and there's going to be 6 nodes here, here, and what is the node spacing going to be? Well, it's going to be oscillating the most rapidly here. So here, this one is just going to be simple. It's just going to be kind of like this. It's going to go up a little here. I think, I don't know why this is going to be shaped more like, so it's going to have its exponential tails here, and then the curvature something like this would be my guess for this one. And this one has 6 nodes. It's going to be oscillating the most frequently here. So very short tail. We're going to have, if it's an even number of nodes, they're both going to come out the same side. And then so we have 1 node, 2 node, 3 node, 4 node, 5 node. That's a little bit too spaced. It's hard to draw these things. So it's going to be it's got to go out more. 1 second. Out more. And then this one's going to go out more like this. Kind of like that. Kind of like that. That's ugh. 1, 2, 3, 4, 5, 6 nodes. All right, E. Oh boy, this one here with the hump. Okay. It goes down like this. And then up past the second one before the third one here. Now we have E equals 0, E equals 1, and E equals for E2. So we got 2 nodes, 1 node, and no nodes. Again, this one's going to be the easy one. E0. E1. Well, it's going to oscillate once. So let's say it's going like this. And then here it's going to come out from here like that. This is lower, so it's going to be a bit more short. So let's say we do something like this. It's going to go up, 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 down. And then we're going to go, maybe it needs to be closer because this is going to be more like this, I think. Maybe it's going to go, how do I, ugh. Oh, what's going to happen in that region there? It's going to bend away. The nodes here. Yeah, I think it has to go very close to this. So let's have it here. Let's say. So it's exponentially increasing here, and then we're curving back to do this. So this is decreasing, curving back, and then this one here, 2 nodes. We're going to have something like this. And then this is going to go like, something like that for this one. Curvature is going to get flatter here. Oh, someone's asking, Scott, if we had 10 days to study classical mechanics and electrodynamics, how should we study it? Yeah, well, what I would do is go through the class, do as much practice as you can, focus on the questions that you're weakest at, and see if you can understand the big concepts. It's always a question of whether you can muster it up in the right time. If you want to have a kind of concise guide to that, I would look up I guess post I did for Cal Newport called, I think the title he used was Mastering Linear Algebra in 10 Days, Experiments in Ultra Learning. So that would be my recommendation. All right, let's try C. Sketch qualitatively the indicated eigenstates of the following potential when the height of the central barrier is V naught equals 0. So, is this a well? Double well. Java applet. Do I have that Java applet? I don't know whether I do. Let me open. Oh. The Java well applet. Where's the double well one? Oh, it's this covalent bond. Okay. Oh, I think it got blocked. Hold on a second. And let's just go over to this one. All right. Oh, excuse me. So what am I looking at here? I want, can I lower the, Yeah, this doesn't have the ability to change this height. No. I don't know whether this is going to be that useful. All right, let's go back to this. Nope. So let's look at these three here. So we have case I is going to be like this. Then E2 is like this. And then we have between E0 and E1. So this is going to be mostly like that. And then the second one is going to be kind of like that. And then our third one is going to be and then our third case where it's much higher than all of them, we're going to have this, this. Kind of like that, right? Okay. Yeah, more or less. And yeah, this is just gonna go. Yeah, more or less. All right, I think that's pretty good. Time is it right now? 1:45. I think I'm just going to take a quick break, maybe half an hour, and then I'll be back to work on problem set 5. So I've got 5.1 that I want to work on after a little break. So just a couple questions before I go. Mohammed is asking, how should we plan a chapter to get mastery? Well, it depends on what's in the chapter and what mastery means. I think you'll need to be more specific. So is how to ask entire organic and inorganic chemistry in 10 days. Well, I mean, if you have a very little bit of time to study, my basic advice is do active recall, focus on the things you're weakest at, and focus on trying to understand the core concepts at work. Those 3 things, it depends on how much time you have. You know, sometimes you're not going to have enough time to do all of that, but I always try to focus on the things that are most difficult, hardest for you. That's the best way to do it. Mastering physics. Well, I'll let you know once I get done this class, hey? All right, I'm going to take a little break, and I will be back in about half